Welcome to the Introduction to Cryptography. Cryptography is the art of securing digital communication. In simple terms, cryptography transforms readable data into a scrambled format. This process protects information during transmission and storage, ensuring only authorized parties can access the original data. This is essential for maintaining privacy and security in our digital world. Let's explore the number theory foundations essential to cryptography. First, we have prime numbers, which are numbers divisible only by 1 in themselves. Examples of prime numbers include 2, 3, 5, 7, 11, 13, and so on. Next, we have prime factorization, which involves breaking numbers down into their prime building blocks. For instance, the number 15 can be broken down into 3 times 5, where both 3 and 5 are prime numbers. Now, let's consider the prime factorization challenge. When dealing with small numbers like 15, factoring is quick and easy. 15 equals 3 times 5. However, when we encounter large numbers such as a 2048-bit number, prime factorization becomes computationally infeasible. It could take millions of years to factorize such large numbers with current computing power. Let's take a look at the RSA Algorithm Overview. The RSA cryptosystem is named after Rivest, Shamir, and Adelman, who invented it. RSA is a public key cryptography algorithm. Its security relies on mathematical foundations, enabling secure key exchange and digital signatures. Public key cryptography allows secure communication without the need to exchange secret keys beforehand. Now let's delve into RSA Key Generation, and we'll start with Part 1. Step 1 involves choosing a prime number, p. We select a large random prime number. For example, let's say p equals 61. Step 2 is choosing another prime number, q. We select another large random prime number. For example, let's say q equals 53. It's crucial that p is not equal to q to ensure the security of the algorithm. Let's continue with Part 2 of the RSA Key Generation. Step 3. Calculate n. N is calculated as p times q. In our example, n equals 61 times 53, which equals 3,233. Step 4. Calculate phi of n. Phi of n equals p minus 1 times q minus 1. In our example, phi of n equals 60 times 52, which equals 3,120. Step 5. Choose e. E must be chosen such that the greatest common divisor of e and phi of n is 1. For example, e equals 17. E is known as the public exponent. Let's discuss the RSA encryption process. The encryption formula is C equals m to the power of e mod n, where C is the ciphertext, m is the original message, e is the public exponent, and n is the modulus. Here's an example. Suppose our message, m, is 65. To encrypt, we calculate C equals 65 to the power of 17 mod 3,233, which gives us C equals 2,790. Now let's move on to the RSA decryption process. The decryption formula is m equals C to the power of d mod n, where m is the original message, C is the ciphertext, d is the private key, and n is the modulus. Here's an example. If our ciphertext C is 2,790, to decrypt, we calculate m equals 2,790 to the power of d mod 3,233, which gives us m equals 65, the original message. Let's explore the security foundation of RSA. RSA security relies on the difficulty of factoring large composite numbers. Specifically, n equals p times q, where n is the composite number and p and q are large prime numbers. The challenge is that, given n, finding p and q is computationally infeasible. Without p and q, the private key d cannot be calculated, ensuring the security of the encrypted data. Finally, let's look at some real-world applications of RSA cryptography. RSA is used extensively to secure the web, enabling HTTPS websites and online banking. Additionally, It's used in digital security for email encryption and digital signatures, ensuring secure communication and authentication in various digital environments. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.